Hello. Now we are going to have a look at similar triangles. So similar triangles means that we have two triangles that have the same angles in them. So another name for similar triangles is equiangular triangles, where we have equal angles. So equiangular. If we look at the triangle XYZ and the triangle KML, are they equiangular? Are they similar triangles? Well, we can see that we have the angle 50, the angle 63, and the angle 67 in both of them. So they are equiangular because their angles are equal. But we can see that they're not the same size. So if we had triangles that had the same angles in them and it was the same size, if this was 20 and this was 20 and this was 15 and this was 15 and this was 10 and this was 10, if they were the same angles and the same size, we might call them congruent triangles. They would be exactly the same. But here we're talking about equiangular. We're just talking about the angles being the same. So these are not identical triangles, but they are in a sense in the same shape. They're in the same form. They change in the same way. And what we will see is that the sides that correspond to each other, the sides that are in the same relative position, their ratios are always the same. Essentially, if this triangle was twice the size of this triangle but the same shape, that isn't the ratio in this case, but it could be. So we have triangles that have the same shape because they have the same angles, but they are going to be different sizes. And if they had the same sides and the same angles, we'd call them corresponding. So what does this look like mathematically? Well, as I say, the ratios of the corresponding sides are the same. In terms of corresponding, again, it means they're in the same relative position in the triangle. The easiest way to read that is that they're across from the same angle. So the side 20, xy, is across from the angle 67. Well, what's across from the angle 67 here? That's going to be the side km, which is 12 long. So xy corresponds to km. They are across from the same angle. They're in the same relative position in the triangles. And likewise for the other sides that we have. So YZ is across from the angle 50 and ML is across from the angle 50 as well. So the ratios of these corresponding sides are the same. So this is written out in the abstract here. The side length xy divided by the side length km. So the ratio, the division of the two corresponding sides would be the same in each case. Well, let's work this out numerically and see is it true. So xy is 20 units long and km is 12 units long. So that's 20 divided by 12 is the ratio of our corresponding sides. And xz is 15 long and kl is 9 long. So that's 15 over 9. That's the ratio of those two corresponding sides. And the same with 10 over 6 for yz all over ml. And what happens when we simplify these fractions? Well, in each case, you have a common factor of 4 here, you have a common factor of 3 here, you have a common factor of 2 here. They all simplify to the same fraction. So they're all in the same ratio. If we simplify the ratio of the sides, we get the same number every time. So if we divide 20 by 12 or 15 by 9 or 10 by 6, we get 5 over 3 when we simplify that fraction. So they're all in the same, the corresponding sides are all in the same ratio. So the ratio of the corresponding sides is the same all the time. So let's look at putting this into practice with our two triangles here. So we have the triangle ABC and we have the triangle DEF. And first thing is, are these ABC and DFE, as I've written it, similar triangles? Are they equiangular? Are they similar? Well, if they were similar triangles, they'd have the same angles. Now I have two of the angles in my triangle in both cases, but I don't have the same ones. So I need to work out, are all of my angles going to end up being the same? Well, for ABC, I have 30 and I have 20. What would be the missing angle here? Well, that would be 180 minus 30 minus 20. So that would be 130 degrees. Well, what about this angle in here? This would be 180 is my total, minus 30 minus 130. So that ends up being 20 degrees. A little bit messy. I'll write that out here. So when we do out our calculations, we see, in fact, the angles are all the same. So ABC is similar to DEF. So yes. And we showed why here and in our diagram. Which side corresponds to AB? So which side in my similar triangle corresponds to AB? Well, that would be the side that is across from 130 degrees. So what side is across from 130 degrees? That's the side DE. That's going to be the side DE corresponds to the side AB. They are in the same relative position in the triangle. So now, this is our most important, or how a lot of the similar triangle questions come up in an exam. Find x. So if we look carefully at ABC and DEF, we can see that one of the sides is missing here. But now that we've established that ABC is similar to or equiangular with DFE, we can use the fact that the ratio of the corresponding sides must be the same. So, what are my corresponding sides? Well, x, or FE, corresponds to 30, or CB, because they're both across from the angle 30. So I have the ratio of x all over 30 must be the same as the ratio of my other two sides that I know. I have DF corresponds to AC, which is 10. So x, I have a obvious common factor of 10 here. So I have x all over 30 is 2. I want to find out what the value of x is. So I multiply both sides by 30. And I get x is equal to 60 units. Now what we can see here is the ratio of the sides. So let's just be very clear. I had my side for my triangle DFE on top in both cases. So I have DFE all over ABC and DFE all over ABC. So the ratio has to be the same from, I have to read the top of the triangle as being from the same, the top of the fraction as being from the same triangle each time. Otherwise I'd end up with it the wrong way up. So x and 20 are from the same triangle and they're the same, they're on the top of both of those fractions. What I can see here when I have that simplified, my 20 over 10 means that DFE is twice the size of ABC. Now, obviously, I haven't drawn that to scale in the diagrams I gave you, but this side, DE would be twice as big as AB. So, because we know we have equiangular or similar triangles, we can say that whatever this side length is, it's twice as big as the side length AB. So that is what we have from our question. And now this is a style of question that comes up in lots of different places, particularly in area and volume questions as well. What we have is a triangle sitting inside of another triangle, and often it will be a right angle triangle sitting inside a right angle triangle, but it doesn't have to be. So are these two triangles, the blue triangle, the smaller triangle in here, is this similar to the big orange triangle that takes up all of that space? Are they similar? Could we show that they were similar? Well, this angle in here, well, to show that they're similar, I should say, we have to show that the angles are equal. So this angle in here obviously has to be the same for both of them because it's the same angle. They both come down to the same corner. The blue one sits into the orange one. So there you have exactly the same shape there, so they have exactly the same angle there. So I'll call that angle A. Now these two angles here are also obviously the same because they're labeled as being right angles. So I'll call them little b and little c. So angle B is equal to angle C because they're right angles. And that's given to us. And the third angle has to be the same. This angle has to be the same because we have because in a triangle we have the same number of degrees overall in both cases. So if these both are the same, if B and C are the same and A is shared, that means the third one has to be the same because you're subtracting A and B or A and C from 180 degrees to get this third angle. So the third angle has to be the same as well. Therefore, it is similar. Now that we have shown that it's similar, are we able to find the value of our side length, the blue side length, y? So we can see our smaller triangle here has a side of y and a side of 10, and our bigger orange triangle has a side of 24 and a side of 15. Well, what sides correspond to each other? What side does y correspond to each other? Well, y is across from the angle D as I have labeled it, which is across, and in the orange triangle, E and D are the same. So the one that would be across from the same angle is 24. So from my blue triangle, I'm going to have my blue all over my orange triangle. I need to keep that the same each time. My side length y all over 24 for my orange or red triangle. So I have y all over 24, my blue triangle side corresponding to my orange triangle side, and 10 corresponds with 15 because they are both across from the angle little a. So 10 from the blue triangle, I have to keep the blue on top both times, corresponds to 15 from the orange triangle. And now can I find my value for y? So I can simplify my fraction here. I have a common factor of 5. I can divide above and below by 5. And with y all over 24 is equal to 2 all over 3. And I can multiply both sides by 24 to get y by itself. 24 divided by 24 is 1. And y, you can take out the common factor of 3 there, or we can multiply it out and then do it. We have 48 all over 3. We get y must be 16 units long. So that's how we can use a fact that our similar triangles are in the same ratio. They are proportionally the same in order to find our missing sides. And a final note on language again, for a congruent triangle, that means an equal triangle, or congruent triangles, equal triangles would mean that they're exactly the same size and the same shape. They have the same angles and the same side lengths. For similar triangles, we just have the same shape. They're in the same proportion. They have the same angles, but they do not have to be the same size. And that's what we need for now.